Welcome back to the deep dive. Today, we're looking at a slice of history that, well, it feels like a spy novel, but it's actually pure mathematics.
It really is.
We're talking about a moment in the late 1970s when the world was scrambling to figure out how to keep digital secrets, and a couple of guys decided the answer lay in a backpack.
Or, more accurately, a knapsack.
Right. The Merkel-Hellman Knapsack crypto system. We are unpacking it today, and we have a really comprehensive technical paper in front of us.
Yeah, it's called Analysis and Mathematical Demonstration of the Merkel-Hellman Knapsack Crypto System. And it's great because it covers the history, the number theory, and, the dramatic collapse of the whole thing.
And it really was dramatic. This wasn't just some minor coding bug.
No, not at all. This was like a battle between two completely different fields of math. You had one side building walls with combinatorics and the other trying to smash them down with, of all things, geometry.
Okay, the smashing part is definitely where I want to get. But I guess we have to build the wall first.
We do.
So let's set the context. It's the mid-70s. The internet as we know it is still years away, but computers are starting to talk to each other. What was the state of the art for keeping secrets then?
It was all about symmetric cryptography.
Like the Enigma machine.
Exactly like Enigma, or the Data Encryption Standard, DES, which was the big one at the time. The rule was simple. If you wanted to lock a message, you used a key. And if I wanted to unlock it, I needed the exact same key.
Which creates that classic courier problem, right? If I want to send you a secret message, I first have to securely send you the key.
But if you already have a secure way to send the key, why not just send the message that way? It was a logistical nightmare. That was the bottleneck holding back global secure communication.
And then, in 1976, Whitfield Diffie and Martin Hellman dropped this paper, New Directions in Cryptography. And they proposed something that sounds, well, frankly impossible.
A trapdoor one-way function.
Right! What even is that?
It was this huge theoretical breakthrough. I mean, they imagined a mathematical process that is incredibly easy to do in one direction.
Like mixing two colors of paint.
Perfect analogy. But it's impossible to reverse, to unmix the paint, unless you have some kind of secret ingredient.
So the idea is that anyone can lock the box using a public key.
But only one person, the one with the private key, can open it.
Now, Diffie and Hellman had the concept, but they didn't have the specific math ready to go yet. RSA came out a year later, in '77.
Right, RSA used prime factorization. But RSA was heavy.
Heavy meaning it took a lot of computing power.
A lot. Modular exponentiation with huge numbers is really computationally expensive. And in 1978, computers were slow, so Ralph Merkel and Martin Hellman wanted something faster.
Something that used simpler math.
The simplest math possible, addition.
And that finally brings us to the knapsack problem. The source calls it the subset sum problem. And I love this because the concept is so simple you could explain it to a kid.
It really is.
Yeah.
Imagine I give you a list of numbers. Let's call them weights.
Okay.
And then I give you a total weight. Your job is to figure out exactly which items from that list I put in my knapsack to get that total.
So if the list is like 2, 5, 10, and the total is 7, I know you picked the 2 and the 5.
Easy with 3 numbers. But what if I give you a list of 100 random massive integers, and I tell you the sum is, 45,892,103. Which ones did I pick?
I would have to start guessing, trying every possible combination. Is it the first one and the last one? Is it the first 3?
And that's the trap, because the number of combinations doubles with every new item on the list. For 100 items, you have 2 to the power of 100 possibilities.
Which is an astronomical number. I can't even picture it.
Nobody can. It would take a supercomputer millions of years to check them all. This is what's known as an n-key complete problem.
Meaning it's easy to check the answer if someone gives it to you,
You just add them up.
but it's impossibly hard to find the answer from scratch.
So Merkel and Hellman saw this and thought, this is a great lock. If I send you a sum, which is the ciphertext, an attacker can't figure out which numbers I used to make it.
But here's the catch, and this is what I was wondering. If the problem is that hard, how does the legitimate person, the receiver, read the message?
Exactly. They can't wait millions of years.
So there must be a special kind of knapsack problem, one that looks hard, but is secretly easy to solve.
Yep.
This has to be the trapdoor.
That is the trapdoor. It's a specific structure called a super-increasing sequence.
Okay, a super increasing sequence. The definition I saw is that every new number in the list has to be strictly larger than the sum of all the numbers that came before it.
That's the rule. A simple example is powers of 2. 1, 2, 4, 8, 16.
Right, because 16 is bigger than 8 plus 4 plus 2 plus 1, which is 15.
Exactly. And the reason this is so special is because it lets you use what's called a greedy algorithm.
This part is so intuitive, you don't have to guess. If I give you a total sum and a super increasing list, you just start with the biggest number.
Walk us through it.
Okay, say my total is 25 and my biggest number is 16. Since 16 fits into 25, I know I must have used it. There's no other choice.
Why not?
Because even if I added up all the smaller numbers, the 8, the 4, the 2, the 1, they only sum to 15. They could never be big enough to substitute for the 16.
Exactly. So the choice is deterministic. You take the 16, you subtract it from 25, you're left with 9.
Then I look at the next biggest number, 8. Does it fit in 9? Yes. So I take it. Now I have 1 left. Does 4 fit? No. 2. No. 1. Yes.
And just like that, you solve the puzzle. You just run down the list once. It's instant.
So the receiver, let's call her Alice, she makes a super increasing sequence. That's her private key, her easy puzzle.
But she can't publish that list. If the public key is visibly super increasing, the whole system is broken before it starts.
Right. Any attacker could just use the same greedy algorithm, so she has to disguise it.
She has to take her nice orderly list and scramble into a messy, random-looking one that she can publish.
And this is where the real trapdoor mechanism clicks into place. She uses modular arithmetic.
Yep. She needs 2 secret numbers for the disguise.
Yeah.
Multiplier, we can call it W, and a modulus, M.
The source has some rules here. The modulus M has to be bigger than the total sum of her private sequence.
Right, that's to prevent overflow, so the numbers don't wrap around and lose information.
And the multiplier W has to be coprime with M. That just means they don't share any common factors.
And that's critical. If they're not coprimed, the math isn't reversible. Alice would scramble the message and then never be able to unscramble it.
Okay, so the formula to disguise each number is you take a private number, multiply it by W, and then take the remainder when you divide by M.
By doing that to every number in her sequence, that beautiful super increasing property is completely destroyed. The numbers get scattered all over the place.
I think we have to do an example. The document walks through encrypting the letter M for Merkel. I think going step by step will make it all click.
Let's do it.
Okay, step 1. Alice creates her private key, a super increasing sequence the source uses. 2, 3, 7, 15, 31, 62, 125, and 250.
And if you check it, 7 is bigger than 2 plus 3, 15 is bigger than 7 plus 3 plus 2, and so on. It works. The total sum is 495.
Step 2. She picks her secret modifiers. She chooses a modulus M equal to 503, which is bigger than 495, so that's good.
And she picks a multiplier, W equal to 184.
Step 3 is where the magic happens. She creates the public key by mangling her private one. Let's take the first number, 2.
Okay, 2 times 184 is 368.
And 368 divided by 503, well, the remainder is just 368. Easy start.
No, the next one, 3.
3 times 184, that's 552.
And that is bigger than our modulus, 503, so we have to find the remainder.
Which is 49.
Right, and she does this for the entire list.
And the final public key, according to the source, is this jumbled mess. 368, 49, 282, 245, 171, 342, 365, and 227.
And if you just look at that list, it's total chaos. There's no pattern. It looks exactly like a random hard knapsack problem. This is what she publishes.
Okay, so now I'm the sender. I want to send the letter M. First, I convert M to binary. ASCII 77 is 0101101.
And that binary code is now your map. It tells you which numbers from the public key you need to add together.
Right, a 1 means add it, a 0 means skip it. So looking at 0101110.
You skip the first number, you take the second one, which is 49.
Skip the third and fourth, then I take the fifth, 171.
And the sixth, 3 of 42.
Skip the seventh and take the eighth, which is 227.
So you just add those up. 49 plus 171 plus 342 plus 227.
And the total is 789.
That is your ciphertext. You send the number 789 to Alice.
And think about this. An eavesdropper intercepts 789. They have the public key. They know 789 is the sum of some of those numbers.
But to figure out which ones, they have to solve the subset sum problem. They have to brute force it, which is impossible. But Alice, she doesn't.
She has the trapdoor. She knows this hard problem is just her easy problem in disguise. And she has the key to take the disguise off.
Which involves the modular inverse.
This concept always trips people up. Since we multiply by 184 to scramble it, we need to sort of divide by 184 to unscramble it.
But you can't just do normal division in modular arithmetic. Instead, you have to find a number that undoes the multiplication. A number U such that 184 times U is equal to 1 in the world of modulo 503.
The source says you find this with the extended Euclidean algorithm, and it turns out the inverse of 184 is 462. So 462 is Alice's secret decryption key.
And here's the magic. Alice gets the message, 789. She multiplies it by her inverse, 462.
Okay, 789 times 462 is a big number, 364,518.
But then she takes the remainder of that, modulo 503.
And the result is 346.
Now pause and look at what just happened. We started with a ciphertext, 789, that was created from the public key. By multiplying by the inverse, we have transformed it into a target sum for the private key.
Wow. So 346 is the target sum for her original super increasing list.
Exactly. So now she just runs the easy greedy algorithm.
Right. On her list, 2, 3, 7, 15. Does the biggest number, 250, fit into 346? Yes. That's a 1.
Remainder's 96. Does 125 fit in 96? No. Does 62 fit?
Yes. Another 1. Remainder is 34.
Does 31 fit? Yes. One more 1. Remainder is 3.
And she follows this all the way down and recovers the binary 01010101. She gets the letter M back.
It's perfect.
It's incredibly elegant. It's faster than RSA. It seemed like the perfect system. So
yeah.
Why aren't we using this to secure our bank accounts today?
Because of a fatal flaw. And the flaw wasn't in the knapsack problem itself. The problem was in the disguise.
This brings us to 1982. And Adi Shamir, this is the S from RSA, right?
Yeah, the very same. He broke the Merkle-Hellman system completely.
Wow.
He realized that the modular multiplication, that scrambling step, it didn't scramble things enough. It was what's called a linear transformation.
What does that mean, linear?
Well, think about that super increasing sequence. The numbers grow very, very fast. They're small at the beginning, huge at the end. When you multiply them by a constant and then wrap them around a modulus, you're shuffling them, yes, but you're not fundamentally changing their relationship to each other.
So the structure of the easy puzzle is still hiding inside the hard puzzle, like a fingerprint.
Exactly. The source explained that because the private numbers are so small compared to the modulus, the public key has a specific kind of density. Shamir realized that if you treat the public key numbers not as a list, but as a grid of points, a lattice, you could actually see the pattern.
A lattice. So we're shifting from arithmetic into geometry here.
We are. Imagine a multi-dimensional grid. Most combinations of points on that grid form vectors, or lines, that are long and messy. But the private key, because of how it was built, forms a vector that is unusually short.
So breaking the code became a geometry problem. Find the short vector in this mess.
Precisely. And while finding the absolute shortest vector in a random lattice is hard, finding a short one in the specific kind of lattice created by Merkle-Hellman turned out to be, well, easy.
And the tool for that was the LLL algorithm.
Lenstra-Lavoie.
Yeah.
The LLL algorithm is a lattice reduction tool. It basically takes a skewed, stretched out grid and it straightens it out so you can see the underlying structure. When they applied LLL to Merkle-Hellman keys, the entire system just collapsed.
The source notes, a modern laptop could crack a key in seconds.
It was a total devastation.
Ah.
And it taught cryptographers a painful lesson. Just because a problem is NP-complete, hard in the worst case, doesn't mean it's hard in the average or specific case you've built. The randomness was an illusion.
There's also a practical problem mentioned in the text, something called data expansion.
Yes, that was another nail in the coffin. In our example, we sent the letter M. That's 8 bits of information.
Okay.
But the ciphertext was 789. To write 789 in binary, you need 10 bits.
So the encrypted message is actually bigger than the original message.
Significantly bigger.
Yeah.
Which is just inefficient. RSA is nearly 1-to-1, so knapsacks were insecure and they were bandwidth hogs.
So the system is dead, a museum piece. But, and this is the part that blew my mind in the notes, the story doesn't end there.
No, it's definitely not over. In fact, you could say we're entering a kind of knapsack renaissance.
That's the irony, isn't it? The math that killed the knapsack is now what's supposed to save us.
It is. We're all facing this post-quantum threat. The fear is that a powerful enough quantum computer will be able to factor the large numbers that secure RSA. It would break the lock that protects pretty much the entire internet.
So RSA is doomed.
RSA and elliptic curve cryptography, yes.
Yeah.
So NIST, the National Institute of Standards and Technology, has been running this competition to find new algorithms that quantum computers can't break. And the winner...
used to break Merkle-Hellman.
The very same. The new standard algorithms, like Cipher and dilithium, they're based on finding short vectors in lattices. They are essentially mathematical cousins of this knapsack problem.
So we've just circled right back to 1978.
We have, but hopefully with 40 years of wisdom. The new systems are built differently. They use a concept called learning with errors. They construct a lattice that's similar to a knapsack, but then they add deliberate noise or errors that makes it impossible for LL to find that short vector.
They learned how to hide the structure better.
Exactly. Merkle and Hellman had the right idea. Hiding a secret in a grid. They just built a grid that was too neat. The new systems are messy by design.
That is just fascinating. It's like Merkle and Hellman built the first airplane and it crashed immediately. But the core principles of flight were right, and now we're building jets based on those same ideas.
That's a perfect analogy. Their failure was arguably more important than their success would have been because it forced the entire field to understand lattices, which are now our best defense against quantum computers.
So let's wrap this up. What is the big takeaway here?
I think the lesson is about the nature of secrecy. We assume that complexity equals security. We think if we just mix the numbers up enough, it becomes random. But math is a relentless detective. If there is a structure, like that super increasing sequence, math will eventually find it.
You can hide the pattern, but you can't erase it.
Not if you ever want to decrypt the message yourself. That's the paradox. You need the structure to read the message, but the structure is the very thing the attacker exploits to break it.
Which leaves us with a pretty provocative thought as we switch our global security to these new lattice systems. Are we sure this time?
That's the billion-dollar question. We feel safe today because we don't know an algorithm that can solve these new, noisy lattice problems efficiently. But in 1978, they didn't know the LLL algorithm existed either.
So is there some super LLL algorithm waiting to be discovered in 2030 that breaks our new systems just as easily as Shamir broke the knapsack?
If there is, let's just hope the good guys find it first.
On that comforting note, we'll leave you to it. This has been the deep dive on the Merkle-Hellman knapsack crypto system, a story of addition, deception, and the eternal geometry of secrets.
Thanks for the great chat.
Catch you on the next one, and keep looking for the patterns.